In this lesson, we're going to take our random effects analysis that we've talked about in the last two lessons and apply it to our our food supplement example. Um, we'll call it our food supplement example. We are trying to evaluate the accuracy of measuring calcium in a food supplement. There are a number of possible labs and a number of chemical assays for calcium. These three labs and three assays that we pick are randomly selected. Each lab will use all three assays. Each assay lab combination or our treatment combination is randomly assigned to 2 of the 18 prepared samples. And then we have our recorded calcium levels here. Okay, this problem is setting us up to be a two-way random effects. Why two-way? Because we have a treatment for assay and a treatment for lab. Okay, we know it's a random effects, a model based on this statement right here. We have multiple labs and calcium assays, but we're only randomly selecting 3 of each. Okay, it doesn't have to be 3 assays in 3 laboratories. I could have had 3 assays in 4 laboratories, but that's not the problem. Then the thing that I want you guys to be careful about is, again, this green statement that each assay lab combination or each treatment combination is randomly assigned to 2 of the 18. This green highlighted statement is just good design of experiment protocol. And I don't want you guys to get it confused with the fact that up here, we're randomly selecting 3 labs from their entire population and 3 assays from their entire population. Once we get those 3 labs and we get those 3 assays, we then still have to randomly apply them to these samples for good design of experiment protocol. Okay? With that intuition of selecting randomly from an entire population, it's also changing our inference in what we're looking at. So we're no longer interested in, is there a difference between just these 3 or just these 3? We're interested in the overall population variance. And so we're using these 3 assays and these 3 laboratories to make conclusions or general assumptions or statements about the overall population variance. Okay? We're going to say our factor B is our chemical, our factor A is our lab. You'll notice I do a little bit of scratching. I noticed some errors after I printed it out, and I didn't want to reprint out this paper, but on your notes, the scratches aren't there, and it's all correct. We have our ANOVA table here. Some people might want to do the actual formal stat, so we have it here, where if we were interested in testing our interaction effect, we have our null hypothesis saying that our sigma for interaction is equal to 0 versus the sigma greater than 0. Again, it's not equal to because variances can't be negative. Our p-value for our interaction is coming from right here, so 0.0803. Since it's bigger than our significance level of alpha equals 0.5, we're going to fail to reject the null and say that there is insufficient evidence to suggest that the lab and assay interaction variance is important or significant. We can then move down to testing our main effects for our lab. So we're going to look at our lab. We'll see that we have a p-value of 0.0318, which would be less than our alpha of 0.005. So we'll reject, and there is significant variability in the calcium between labs. Okay. Then again, if you wanted to, we can do the main effects for our assay. We'll get the p-value from here because that's what our assay p-value. And we'll fail to reject because this is greater than our significance level to suggest there isn't enough evidence to suggest that there's significant variability from assay to assay. Now, we do not do a Tukey's or multiple or any type of multiple comparison tests in this random effects analysis because, again, we're not interested in how these three assays or laboratories are different. We care about the overall. So a follow-up analysis for our random effects is to look at and estimate our variance components. Here we have our variance of our epsilon, so the background noise, which is just from our MSE, which is 0.375. We got this number by going to our source of error. My R users, it's normally residuals, and we just pulled this number off right here. Okay, that's related to this. Our variance component is then for our interaction is MSAB minus MSE divided by 2. Remember, or divided by little n. Remember, n is our number of replicates. In this example we had up here, we have 2 replicates per each assay laboratory combination. So to get this number, I go to our ANOVA table. I pull out the MS for our interaction minus the MS for our error, and then I divide by 2. That's how I got this number. Same thing, but with our effects, or our main effects, it's whatever our main effect is minus our MS of our interaction. And then we're going to be dividing it by n times A if it's for B, or n times B. Again, these formulas are in your notes previously. Something else that we might want to be interested in is looking at the proportion of variability from each of these components. How we do that is we first have to calculate them, and then we can sum them, and pretty much doing the proportion is the sigma of B divided by the sigma of Y, just working with proportions. What we see from here is that our proportion for our A, which is our lab, is the largest. So if we multiply it by 100, it's about 62% of our variability comes from our lab. What this could tell us from a practical standpoint, this makes sense also because we tested it, it made sense. But from a practical standpoint, we might want to go to our labs and see why there's so much variability from lab to lab. Maybe we need to, when we get there, we see the trainings of these different labs aren't the same, so we might need to implement a training protocol. So whenever you're making these conclusions, you always have to think practically about it. Also, remember that if any of these terms turn out to be negative, because mathematically that is possible, you set it equal to 0. There are some estimates that can restrict you so that you don't have to worry about that, but using the expected mean squares like we have, we might incur some negative variance. All you need to do is set it equal to 0. With that, that is a brief overview. Now I recommend going to go watch either the JUMP or our video to help you implement this and complete your homework.